Okay, so we have this professor head right here, and we need to determine a few things. Kind of the first couple parts that I have as far as the goal that we want to do with this circuit is we want to get it from the nasty look that it has right now into a form that looks more manageable. And toward that end, the first couple of steps there, we're supposed to try to identify nodes where current can split. That's the first thing. There will be other nodes that we won't identify where current doesn't split. I think I talked about that a little bit last time, that the nodes that's really important for you to kind of identify and know how to deal with are the ones where there's a possibility that the current could take multiple paths when it gets to those type of nodes. Okay, so we'll identify those. We'll identify any short circuits. I'm going to talk a little bit about what a short circuit is and how you can identify them and what you can do if you find one. Next, we're going to redraw this circuit neatly, and then we're going to remove any of the shorted branches. That may be a little bit of a preview of what you're going to get to do if you find a short circuit somewhere. Okay. Next, we are going to find the equivalent resistance of this resistor network. We'll find the power supplied by the battery. We'll find the voltage drop across the 40 ohm resistor, and we'll find the power dissipated by the 30 ohm resistor. This gets right into the nitty-gritty of this circuit, and we'll try to get all of these pieces of information found. Okay, starting with part A, we're going to identify nodes where current can split. How do you know you have a node where currents can split? Okay. Generally, it's a spot where multiple wires maybe branch at a particular point, right? So, like for instance, I could say I have a bunch of wires right here. They branch a few times, but all of this stuff, I can highlight all of that stuff without actually going onto a particular circuit element. That's just wire, right? So any place you can put your pen down and highlight a bunch of stuff and all you got is wire, all wire connected to itself, then that means you've got a node. And so all that yellow stuff that I just drew right there is a node, and it's one where current can split because it has multiple branches. Does that make sense? Where else do I have a node? Okay, how about the other side of the battery, right? I can start drawing over here, I can start highlighting this stuff, and as long as I can go, I go as far as I can go to the point where I run into circuit elements. So I run along here, and I take my furthest extent that I can until I run into a circuit element. Okay, so all that stuff that I just highlighted in blue, that's another node of this circuit. Okay, and it's, it doesn't really matter what shape all of those wires take. What defines the circuit is what circuit elements connect from what node to what node, right? And any number of ways that they can look when they do that, but it'll be an equivalent circuit as long as we get the same circuit elements connected to the same nodes whenever we redraw the circuit. Okay, where else do I have a node where current can split? Okay, up at the top left, you see a little spot where I might have some glasses. Where I think this is where you're talking about.
30 to 70, and then to the right of that.
Yeah, so like there's a spot up here, that kind of goes up to there and then over to here. Well, this is kind of interesting. If I actually keep going all the different directions that can go, that goes all the way down to there. Right? Well, that's kind of interesting. Okay. Where else do I have a node where current can split? Okay, on the right side, there's another spot where that can happen. So, like over here. All right. And I would go up to those, and I'd go up to here, and I go right there. Okay. Technically, I have another place where current could split, and it'd be right here. That would be another node. Okay. So using my highlighting colors here, I have identified nodes where current can split. All right. Now, this is the next piece. The next piece is identify any short circuits. How can you identify a short circuit? What's something that would be a marker of a short circuit. Well, let me say it this way. Let's actually look first at the left eye, the one that's on the right side from what we're seeing, right, of this guy. Okay, this eye right over here. Tell me this. Is there anything that looks like it would drive current through those resistors? Okay, in other words, the thing that's driving current is the battery. The battery's pushing current along. And in order for current to flow, there has to be a difference in voltage from one spot to another, and it pushes the current along. Okay? When you look at this, is there anything that's pushing current through this little loop? As a matter of fact, there might be stuff that's pushing current like maybe along this way, perhaps, but as it goes through here, there's no reason the current would want to flow through through the spectacles here, right? That won't happen. And the reason that won't happen is that there's a shorter path for it to go through. In other words, an easier path for it to flow through, because over here, right where it kind of touches the side of his head, right there is zero resistance. So all of the current's going to go through the spot where there's zero resistance rather than trying to go through this stuff where there is more than zero resistance. Does that make sense? Okay. It'd be like if there was a checkout lane at Walmart where you had to stand in line and check out, and there's another lane where they're just letting people walk right out of the store. Which would you choose? I doubt anyone would go to the checkout lane. All of you would go out the lane where you could just leave the store, right? So that's what's going on there, is it gives this path where current can flow, and it goes right through here and continues along, and there's no reason that any current would want to flow in those two resistors right there where that loop is set up, okay? I think what you're saying is if it was set up differently, right? Let me kind of change this up just a little bit. He's saying if for some reason it was set up to where there was a resistor right here, and then this went to one side and this went to the other side, changes the game, right? Because now some of the current would want to go through the resistors on the left, and some of it would go through the resistor that I just put right there. That is different. That is no longer a short circuit. But the fact that this right here basically represents just wire, it's going to take that path. There's no reason that the volts or the current is going to want to flow through that other piece. Here's one of the other ways that you know. If you see that a node goes up to two sides of a little loop like that, again, there has to be the same voltage on that little green nub as the other little green nub, because it's at one node. They have the same voltage on them. So there won't be any voltage to drive current through those resistive elements. Does that make sense? All right. So what do we do with that? If no current goes through that little loop right there, what can we say about it? It's irrelevant. We can eliminate it, and it has no bearing on the rest of what we solve for. We don't even have to look at those resistors because it has that short circuit right there. Can you guys see any other place where we might have something similar?
The other side.
Yeah, the other eye, right over here. All of that is irrelevant because the current will actually flow. All of it will flow through this little leg right here. None of it's going to want to go here because that has greater than zero resistance. Right? So there won't be any current that flows right there. All of it goes right through there. Okay? So what we've just done is we've identified two short circuits. I'll give you like 10 seconds. Can you look through it and see if there are any other short circuits? And maybe one of the ways you can discipline your mind to try to think about finding short circuits is, are there any other places where the same color of highlighting that I put on there whenever I identified the nodes, are there any other places where that highlighting goes up to two sides of the same kind of resistor network with nothing else also on that resistor network? Okay. A lot of you are thinking, we better find something because he wouldn't be asking the question if there wasn't something. Is anyone thinking that in their mind right now? Or maybe I'm just devious and just asking the question to try to force you to think. Go with option B. That's what I'm doing. There are no other short circuits in this circuit. Yes? Yep. Okay, what's happening is current wants to flow from the positive side of that battery to the negative side. And it will find any paths that it possibly can to go from the positive side to the negative side. And right now it's a little bit difficult to look at that and see all the different directions it's going to go. But the next step where I redraw this circuit neatly with shorted branches removed is going to fix that for you. Okay? And I'm going to show you that you can do this too, and it's not actually that hard to go from something really messy like this to something that's easier to understand. Here's how I recommend you do it. I recommend you start with, if you have a source. Most of the problems we give you, at least in this class, generally just have one source. What do I mean by source? The power source, like a battery, right? Start with that, and just so it always kind of looks the same. There's no reason it has to be this way, but it helps you think about it if they tend to look the same. I usually put that over on the left side. Okay? So I'm going to put in this 80-volt power source over here. Okay? And from there, I'm going to extend one lead up like this and start going across like this, and another lead to go down like this. And I think I might need to give myself a little more space. All right. Okay, we're going to start here. Because ultimately what we need to do is find all the different paths that we can get from the positive side of this source to the negative side. And so let me go ahead and I'll start also by saying this is my yellow node that I'm setting up here. This is my blue node that I'm setting up down here. I'm just drawing it in a different way, but they're not different. Those are the nodes I'm representing here. And what I'm drawing up here is an equivalent circuit to the big messy thing. Okay? So what's one way that current could flow from yellow to blue? How about the 50 ohm? That's not a complicated path. All it's got to do is get through the 50 ohm and down to here, and it made it. Okay? Notice here I can continue to highlight, whoops, that's not the color I wanted. Continue to highlight these nodes so that they kind of make sense. Okay? All we've done there is we've shown that this current can flow through that 50 ohm resistor right there. Is that the only path for it to take? What's another path it could take to go from yellow to blue? It could go through the 60 ohm. So we make another path. We make a parallel path where the current could go from yellow to blue. Just like this. Okay, let me label that as the 60 ohm. All right. Are there any other paths that current could take going from yellow back to blue? Okay. There's another one where it can go, let's think of another way we could go from yellow to blue. We could trace along here, go through the 40 ohm, come up along here. We could go through the 100 ohm and go then through the 10 ohm and get back to blue. Right? So let's make that path. Right? What that would look like is we would come from yellow. Right? Then we would go through the 40 ohm. Then what happens? Is there another split? So this is a 40 ohm. Why did I pick going through the 100 ohm when I made it up here? There was a split, right? I could have gone up that way. Okay, so let me actually show here that I can split this And some of this current could go this way, where it goes through a 100 ohm resistor. Then it goes after that through the 10 ohm resistor. And then from there, where does it go? After the 10 ohm, the current comes back to, yeah, that blue node, right? So you see there, it goes back to blue. In between here, think about this. Okay, I showed yellow going up to that 40 ohm resistor, and then we had another node that branched, and I colored that a different color, right? That was that green node. Okay, and remember that green went all the way up along here. Okay, but that green node branches to another way that we can go around and get back to blue, right? It can go up through here, go through the 30 ohm. None of it will go through this, eyeball stuff over here. It'll go around his ear and come down here, go through the 70 ohm resistor, and back to blue. Okay, and we know that because we're eliminating the short circuits. Okay, so anyway, what that looks like here is that we're going to go and have an alternate path here where it goes through one resistor, that's the 20 ohm. Then it goes through another resistor, that is the 30 ohm. And then it goes through another resistor, that's the 70 ohm. And from there it gets back to blue again. Okay, and you might notice there the green is what feeds this side of that path. Okay, this big nasty circuit that I have up here, these are equivalent. The reason they're equivalent is they have the equivalent types of components that go from nodes that are set up equivalently, right? So there's no difference between the big nasty thing up there and now this much neater circuit that I have right here. Okay? So now what do you want to do? Is that we just finished part C. We made this circuit right here. What's the next piece? Okay? We need to find the equivalent resistance of the resistor network. So we have a few different things up our sleeve for that. First of all, we can maybe redraw this thing. I'm going to just make a quick copy and paste here. Let's see. So I'm going to redraw this with let's see. There we go. Anytime we have some series resistors, right, what can we do with the series resistors? Okay, we can redraw the circuit with the series resistors put in, added together, right? So kind of our first step is take those series resistors and replace them with an equivalent resistance value of what? 110 ohms. Down here, we can replace all these resistance values with, okay, that's going to be 100, 120. Okay, so I take all those and replace with 120. All right, so what's the next step after that? Okay, so I'm going to copy this again and paste it down here. All right, and what we do next is we combine any sort of groups of parallel ones that we have. The first place where we need to do that is with this group right here. Okay, so I need to replace that group right there with an equivalent resistance. And what would that equivalent resistance be? It'll be 1 over 1 over 110 ohms plus 1 over 120 ohms. Okay, so 1 over 110 plus 1 over 120. And this gives me 57.931, or 391, excuse me. So how do I replace everything that's in the red there with that? Okay, I get rid of all this, and I replace it now with just one resistor that goes down through there that has a value of that 57.391 ohms. Okay, so what's the next step then? I'll just redraw it now. Now the next step is we basically have this circuit, okay, where I have 50 ohms here, I have 60 ohms here, and I have what for the last one? Okay, I add together my 40 ohms with my 57.391 ohms. Okay, and that gives me 97.391. And this again was 80 volts over here. Okay, and I'm almost there. What's my last step? So what I did here, just to trace it, I went from here to here, went from there to there. Now I've gone from there to there, and I'm going over here. In this last step, I've got my 80 volts as my source, and it goes through just one resistor. That's my equivalent resistance. Okay, I call that REQ2. And what is REQ2? 1 over 50 ohms plus 1 over 60 ohms plus 1 over 97.391 ohms. Okay. All right, so I do 1 over 50 plus 1 over 60 plus 1 over my previous answer. That gives me 21.31 ohms. And that is the answer to part, what was it? D. We just found the equivalent resistance of the resistor network, 21.31 ohms. Okay, so what then? Power dissipated, what did it say? Find the power supplied by the battery. All right. So there's a couple of different expressions we have for power. One of them is what? V squared over R gives us power. And we happen to have, in this case, voltage and resistance. And so that tells us that the power dissipated by this whole circuit is going to be equal to 80 volts squared over this equivalent resistance of the whole thing, 21.31 ohms. Okay, so that gives me 80 squared over that previous answer, which is 300.9 0.38 units. Okay, this will be watts. You might know that just because you've done this before. If you don't know that because you've done it before, what this ends up being is volts squared per, an ohm is a volt per amp. Okay, what this ends up giving you is volts times amps, and that's watts. Okay, so in case you wanted to remember how those units came to be, because an ohm is a volt per amp. All right, so we've done that part. We figured out how many watts the voltage source, the battery there, is supplying. So we've done that. Now we need to figure out what is the voltage drop across the 40 ohm resistor. Okay. How do we get that? Let me ask this. If you knew the current flowing through the 40 ohm resistor, would you be able to find the voltage across it? Okay. Is there any way we can figure out what current flows through the 40 ohm resistor? Okay. Let me just call that I. I'm looking at, this is a good spot right here where I can look at that current, because that's the same current that would flow in this leg right over here. How do I know that? Yeah, because those are equivalent circuits, and we're talking about equivalent legs of the equivalent circuit. We're just whether or not we combine the resistors together. All right, well, how much voltage do I have across that 97.391 ohm resistor right there? 80 volts. How do I know that? Yeah, look at this. This entire node, right, relative to this entire node, you know, anywhere I put my multimeter across those two nodes, it's going to be 80 volts. Okay? So that means it's 80 volts going across that 97.391 ohm resistor. Okay? And so that tells me that I can do this calculation. I is going to be equal to 80 volts over 97.391 ohms. Please don't mistake what I'm doing here for the amount of current flowing out of the source, right? This is not the amount of current flowing out of the source. This is only the amount of current flowing in that leg that has the 40 ohm resistor in it. Okay, so don't misunderstand what I'm doing here. All right, so now that I've got that calculation, which turns out to be 80 divided by 97.391, that gives me 0.8214 amps. Okay, how do I use that? Okay, that is this right here, 0.8214 amps. What I'm trying to figure out is what's the voltage just across just that 40 ohm resistor. Is that another good place where I could use, maybe I'll call that V sub 40 here, all right? Is that another good place where I could use Ohm's law? All right, V sub 40, V equals IR, so it's going to be equal to 0.8214 amps times what? 40 ohms. So what do I get there? Okay, yeah. 32.86 volts. Great. That's how many volts go across the 40 ohm resistor. Okay. By the way, in the interest of time, I'm doing this quickly so you see a lot of stuff on the screen all at the same time so you can know what I'm referencing. This is not how you should do your homework, okay? Your homework should look different than this, but I'm trying to make the whole big picture look obvious all on the screen at the same time. That's why I'm using my space the way I am. On your homework, probably a better way to do it is to try to make it more sequential, okay? But just figured I'd mention that. All right, so we just now figured out the voltage drop across the 40 ohm resistor. Now what do we need to do?
Is that the drop or is that just the voltage? Is the drop actually 80 minus 32?
Okay, the question just asked was, is the drop 32.86, or should we subtract that from 80, or, okay? Here's the thing, voltage drop is voltage, okay? So we typically, or a lot of times we'll use the phrase voltage drop when it's with respect to a resistor, because the idea of a voltage drop generally means that you are dissipating energy rather than sourcing it, okay? In other words, it's sitting there making heat is what it's doing. That's where the energy's going, okay? So when I say that's a voltage drop, that's usually referring to an element that is dissipating energy rather than one that's sourcing it. We typically think of voltage rises as the things that are sourcing voltage, whereas the things that are sinking, this energy are drops. That's just how the terminology tends to get used. In general, I don't always use the phrase voltage drop. A lot of folks do, but I a lot of times just say voltage. Okay, so that's the voltage across the 40 ohm resistor. Now we need to find the power dissipated by the 30 ohm resistor. Okay, what do I need to do that? Would you agree that if I knew the current that flowed through this leg right here, okay, I'll just call it I2, because we already used I, right? I'll call it, this is another current. This is a different current. If I know the current that flows through that path right there, could I figure out the power dissipated by the 30 ohm resistor? I see a lot of heads nodding. Okay, that's good. You can do that. What does it take? Yeah, I heard someone say power is I squared R. If you know I, which is the current going through a particular element, and if you know the resistance of that element, then you can determine the power dissipated by that element. So now the question is there something I can do to figure out the current that flows through that leg right there? Okay. The answer is yes, you can. All right, there is something we can do. Here's what we can do. We know that from here to here, we had a 32.86 volt drop going across that 40 ohm resistor. Do you agree with that? That was our last step. Well, what does that mean for how much voltage drops across this 120 ohm equivalent resistance right here? Should be, right, there's a loop that we're identifying right there. It goes from 80 through this 32.86 and then through the 120 back to 80. And what did we learn last time? Sum of voltages around any closed loop in a circuit has to be 0. We have an 80 volt rise with a 32.86 volt drop. What are we left to drop on the 120 ohm? 80 minus that, right? So 80 minus that answer gives us 47.143, okay, volts that will drop on that leg. And by the way, that's the same voltage that will drop across the 110. Same voltage across the 110 as across the 120 right there. Okay? Well, if that's the voltage drop, then what's the current? Because this current that we can find right here is I2 that I identified on that other drawing. Okay? So what would that current be? I2, just use Ohm's law, right? It's going to be equal to V over R. Agreed? So 47.143 volts over 120 ohms. That gives me 0.393, we'll say. That's in amps. But that's not really what we wanted. How do we determine the power? I'll call that maybe power P30. I'll put that right here. What's our formula? I squared R. So we put in 0.393 amps squared times what resistance? 30 ohms. Okay, and I believe I had that number up here still. So I can take that answer squared times 30. Okay, so that one resistor right there, the 30 ohm resistor, dissipates 4.63 watts. All right. Now, if you're curious about those units, what we have here, we basically have amps squared times an ohm is a volt per amp. This ends up giving you volts times amps, which is watts. Okay, so that's if you're curious about how those units work out for that expression right there. That's why it turns out to be watts. All right, I know that wound up to be kind of a messy screen, but I wanted to get it to where you could see all the different permutations of the circuit at the same time. Okay? Here's my recommendation when you approach a problem that looks pretty rough like this one. Okay? My recommendation is that you do not spare on the number of circuits that you draw. I would definitely draw each step of I'm going to reduce it from this to this, and then draw the next one from this to this, draw next one from that to that. Because you'll notice I kept on going back to old circuit figures that I drew so that I could actually say this is the current that I'm trying to find, or this is the voltage I'm trying to find at each step along the way. And having these visuals that you can use to understand that is helpful, in my opinion. All right. Questions? Yes, sir. Okay, where that came from was Kirchhoff's voltage law that we learned last time. It says that around any closed loop, the sum of your voltage, really voltage changes, basically the sum of your rises has to equal the sum of your drops, right? What we have is we've got a loop. I'll do it here with a different color. We have a loop that goes around here, and around here, and around here, back to here. That's a loop. Okay? That means we have an 80 volt rise with a 32.86 volt drop for the 40 ohm resistor. We have to make up the difference over there with the 120 ohm resistor. So it's basically 80 volts minus 32.86 volts across the 40 ohm resistor. That leaves you with 47.143 volts across the 120 ohm. But it's the reason we know that is because of Kirchhoff's voltage law. All right, any other questions? Fantastic. Did you guys think that was going to be worse than it was? Or was it pretty bad? Okay. The trick is in drawing all of your reductions of your circuit. You do an equivalent, do another equivalent, another equivalent. If you draw all those out, it's not too bad to get through even a messy thing like this. All right. Well, thank you for your attention.